Quiz 18.1 deals with entropy. And entropy is kind of an abstract idea at first, but it actually is grounded in rigorous mathematics. Remember in lecture we talked about how it started as this thermodynamic potential, but we're just going to talk about it qualitatively for the first part here, and look at reactions and identify whether the change in entropy is positive or negative. And so remember, we have like this hierarchy of phases, and entropy will increase as you go up and decrease as you go down. We know that delta S is equal to, I'll say Q over T. So if we're heating something up, then Q is going to be positive and the entropy will increase. So higher temperatures are higher entropy, lower temperatures are lower entropy. And then delta N is going to be important. So if you produce more moles of product than you have moles of reactant, then you'll have a higher entropy. And this is particularly pronounced when you have aqueous or gas phase reactants which occupy a large volume. And so let's just look at question 1 here. Okay, so this first one, H2O gas to H2O liquid, that will have a negative entropy. Maybe I'll just write them all up here. Okay, so we'll have a negative entropy for the gas to liquid transition. Solid to gas transition, the second one there, will be positive. Carbon dioxide solid going to carbon dioxide gas is the dry ice reaction. Just have dry ice turning into gas, and that will be positive. The next one, 1 nitrogen plus 3 hydrogens forming 2 ammonias, we've gone from 4 moles of gas to only 2, so that's a negative. And then the sodium carbonate plus sulfuric acid reaction, well, what we have is aqueous on the left and gas on the right. And so the gas phase is going to be more entropic than the aqueous phase because it occupies a larger volume. And in addition, we've gone from 2 to 4 moles of things in general. So this one is definitely positive. The sodium acetate, aqueous precipitating out into sodium acetate solid, that will be a negative. And when I was doing that hierarchy of phases, I should have added that aqueous is somewhere next to liquid. It's got mobile particles. They're able to move past one another, and they occupy the volume of the liquid that they're dissolved into. So it's sort of on par with liquid. Where are we? Now we're at the valve on a pressurized gas tank is opened and the gas comes streaming out. So there's no phase changes, no reaction, but you have the gas expanding to occupy a larger volume. That will be a positive entropy change. And then a sample is taken out of the freezer and left on the counter for 20 minutes. Oh, sorry, I never scrolled down. Let's scroll down a little bit here. There was the sodium acetate precipitating out, and then the valve on the pressurized tank. Then finally a sample taken out of the freezer and left on the counter. What's going to happen? It will warm up to room temperature, and even if nothing else changes, the system will have its entropy increase as it is warmed. Okay, and this quiz, the next part here is maybe not the most important part for you to know about entropy from a chemistry perspective, but me being a physical chemist, I couldn't help but look at Boltzmann's definition of entropy and the role that like probabilities and statistics will play in our understanding of entropy. So Boltzmann said that entropy is equal to some constant. It's a lowercase k, but since there are so many k's in chemistry, I like to put a b there for Boltzmann, times the natural log of W. And we're going to call W the number of microstates. And you can get more sophisticated about defining W later on if you go on to take 3610. But we'll call it the number of microstates. And so this first one, tossing a 6-sided die, W is going to equal 6. You can roll a 1, a 2, a 3, a 4, a 5, or a 6, and those are the only available microstates in that system. And so S is going to equal Boltzmann's constant. I guess I should give you the value here, so you can just look it up. Oh, I don't have it. Never mind. But you can look up Boltzmann's constant. It will have units of joules per Kelvin, which are kind of weird at first. Like they don't make as much sense as, say, the speed of light is meters per second. That I can understand. What is a joule per Kelvin? But those are the units of entropy. And as we deal with entropy in lots of equations moving forward through chapter 18, you'll see that those units are going to be important to keep track of. For example, they're joules instead of kilojoules, and so we'll want to reconcile our delta S's with delta H's and other things that are commonly expressed in kilojoules. Okay, so if I take Boltzmann's constant and multiply by the natural log of W, then I'm going to get 2.47 times 10 to the negative 23rd joules per Kelvin. Okay. Well, what if I add a second die? So now we're rolling 2 dice. So we're going to toss 2 6-sided dice, and we're going to consider the dice to be distinguishable. Again, I didn't mean to make this so like esoteric about little points about probability, but the fact that the dice are distinguishable means, for example, that a combination of 2 and 1 is a distinct different microstate compared to a combination of 1 and 2. So we would consider these 2 different microstates because here dice A has the 2 and dice B has the 1. Here dice A has the 1 and the die B has the 2. So anyway, when you have distinguishable independent dice like this, then W is going to equal 6 times 6. That will equal 36. And we'll just plug W into our equation here. We get 4.95 times 10 to the negative 23rd joules per Kelvin. Taking the natural log of W makes the entropy climb not quite as fast as you would have thought. This is far less than 6 times our last value. Okay, now this next one is starting to look a little more like chemistry. So if you have a 10 milligram diamond and you cool it to near absolute zero, then the only excited states accessible at this temperature will be a nuclear spin state. If you don't know what that is, don't worry. It's like energy levels in the electronic energy levels we learned about, S, P, D, and F, etc. Well, those are energy levels that are related to the electrons of an atom. Well, the nuclei also have energy levels. We don't learn about them in this class, and their energy differences are usually very, very, very small or very, very, very large. And so we don't encounter any interesting or important effects from nuclear spin states in most of our chemistry reactions. But you will learn about them eventually as you move on and learn about NMR spectroscopy and such. But anyway, so the only excited state accessible at this temperature is a nuclear spin state. which each carbon atom has an equal probability of being in the excited state or the ground state. And we're going to consider these carbon atoms to be distinguishable. So W is essentially going to equal 2 because there's an equal probability of two different states, ground state or excited state. And we'll raise that to the power of n. N is the number of carbon nuclei or carbon atoms. So let's figure out n. We'll have 0.0100 grams. Carbon is 12.011 grams per mole. And 1 mole is 6.022 times 10 to the 23rd individual carbon atoms. And so that's 5.012 times 10 to the 20th carbon atoms. A lot of carbon atoms in just a teeny tiny diamond. Okay, and we'll go ahead and put that in here. S is equal to KB ln of 2 raised to the power of 5.012 times 10 to the 20th. Now I invite you to put that into your calculator. Whatever calculator you have is going to spontaneously explode if it tries to calculate that number. But thankfully, because this is in a natural log function, we can actually take that exponent and bring it out front as a coefficient. So this is going to equal 5.012 times 10 to the 20th times the Boltzmann constant times the natural log of 2. Now that's something your calculator can handle just fine. And that's going to give you 0.00480 joules per Kelvin. And finally have a system that has an appreciable amount of entropy. Okay, and this next one is looking at the arrangements of gas molecules. And so if we have a chamber with 2 halves and 4 gas particles, 4 helium atoms, and they're indistinguishable, then how many different microstates are there? How many different ways can we arrange those gas particles? We could have all 4 of them on one side. We could have 3 of them on the top and 1 of them on the bottom. We could have 2 of them on the top and 2 of them on the bottom. We could have 1 on the top and 3 on the bottom. Or we could have 4 of them on the bottom. So this is a total of 5 microstates. And of course this is an idealized simplified system. Like, why does the chamber only get cut in half? Like, what if I had the particle up in the corner versus by the left side? And we're simplifying and saying that doesn't matter. We're just going to consider the different states as being when the particles are in the top half versus the bottom half. Anyway, this gives us a W equal 5. And entropy S is going to equal 2.22 times 10 to the negative 23rd joules per Kelvin. Which is just a little bit less than our 6-sided dice. And now, the whole key to these problems is finding W. And as W gets to be a little bit more prominent in 3610 and beyond, as you learn statistical thermodynamics, it's always about finding the value of W. Okay, so this last question, we have 4 different gas particles. Maybe one's a helium, one's a krypton, one's a neon, and one's an argon. They're placed in a chamber with 2 halves, and each atom has an equal probability to be in either half of the chamber. Only this time, because the atoms are different, they are distinguishable. And so that means we might have more than one microstate for each of these sort of general categories. So there's only really one way to have 4 atoms in the top, so that one stays the same. But consider this one. If I have 4 atoms, A, B, C, and D, well, I could have A down here and the rest up there. I could have B down here and the rest up there. I could have C down here and the rest up there, or I could have D down here and the rest up there. So there are actually 4 microstates that have this general configuration where each of the different distinguishable atoms is just taking a turn in the bottom. And there's some symmetry here, right? There's only going to be 1 of these, and there will be 4 of those. Now this one is a little bit tricky, so let's just consider the different combinations of 2 atoms that we can have in the top, and then the other 2 will be in the bottom. For example, I could have A and B in the top. I could have A and C in the top. I could have A and D in the top. Now, B and A, that's the same as this one. Although the atoms are distinguishable, they're both in the top. You know, the position left or right here isn't actually meaningful. This is just a collection of atoms which are in the top, and this is the same microstate then. Having B and A in the top is the same as having A and B in the top. But we can have B and C. I'm about to run out of space here, so I'm going to reclaim that bottom part of my chalkboard. We can have B and C. We can have B and D. And we can have C and D. So those are all the different ways that we could arrange this, and so we would have 6 different microstates which match this configuration. If we now consider that pressure, air pressure, does not depend on the identity of the molecules, just on their numbers and volumes and temperatures, that's what PV equals nRT is really saying, that the pressure depends only on those state variables, then we would expect 6 to be the most probable, we would expect this to be the most probable macro state. That is, we would expect that the pressure, if we put a pressure gauge in both halves of this chamber, we would expect those pressures to be equal. And then occasionally you'll have a fluctuation with higher pressure in the bottom and higher pressure on the top, and very rarely indeed you'll have 0 pressure on the top and even higher pressure on the bottom, or vice versa. And remember, the most probable macro state refers to the configuration with the highest number of microstates. That's not a part of this question, but I just wanted to throw that out there. Okay. Now all we really want is to count up our microstates to get W, and we've got 4 plus 1 is 5, and there's another 5 and a 6, so W is equal to 16. And so S is going to equal K times the natural log of 16, 3.83 times 10 to the negative 23rd joules per Kelvin. And that's it for quiz 18.1.